Swayam Prabha. Digital India. Educated India.
We have discussed so far systems where bodies rotate about an axis, and we have seen the effects of unbalance present, how it can develop dynamic forces on the supports. We have also looked into the matter of balancing such systems. Next, we have to now consider other types of mechanisms and machines where the components do not involve only in rotation, but have other kinds of motions. So, of course, the problem of balancing or even the problem of investigating the balancing of a mechanism is a very complex problem. However, in a very large number of situations, mechanical machines or systems or engines, they employ a slider crank mechanism. So, next what we will do, we will take up those cases where the system consists of a single slider mechanism, which we call a slider crank mechanism in kinematics. So, these single slider machines are very common, large types of machines, then compressors, engines, they all employ this mechanism. So, I think it will be appropriate to take up this particular case and investigate its unbalance, and also to look into the ways and means of balancing the unbalance present. Now, a typical single slider machine will look like this. This is the crank which rotates with a say constant angular velocity as a special case, omega, which is constant. This rod or object which connects the crank to the slider, this is the slider, is called the connecting rod or coupler. Or coupler. So, I hope you are all familiar with this mechanism where the crank continuously rotates and the motion of this crank is transferred to the slider with the help of the connecting rod, and the slider executes a reciprocating motion. So, we find that here there is one body, that is the crank, which is making a pure rotation. So, it is a rotating body, whereas the slider is executing a pure translatory reciprocating motion. So, it is a reciprocating body, and the connecting rod, which causes the serious problem, is a general floating body which executes both rotation and also translation. Of course, depending on the situation, sometimes this can be the input, like a compressor or a machine, stamping machine, punching machine, sewing machine. This is the input member where power is given, and this is the functional part which does the job. In case of engines, for example, on the other hand, this is the input body where gas pressure produces this kind of motion, which ultimately rotates the shaft connected to this crank, which we call the crankshaft, and that drives the output system. So, here the dimensions normally are such as we have shown. Say here the crank radius is r, and the CG of the crank is, say, here. The connecting rod, its center of mass is somewhere here, and of course, the center of mass of the slider is here. It really is not important, because for a translating body, the location of the center of mass is of no consequence. The length of the connecting rod may be L, and another important thing which you should notice in this case, that we have treated a case where the slider is reciprocating along an axis which passes through the origin O, which is generally not the case. It could be here or here, that means with certain amount of offset, but since offset cases are not very frequently used, so we are using the most frequently used situation where the offset is 0. Now, so therefore, we have to keep these things in mind, that offset is 0, and also we have to keep in mind that the connecting rod length and the crank, this ratio R by L is less than 1, which is also generally the situation. So, we have seen that connecting rod is a purely crank is a purely rotating body, slider is a purely translating body, and connecting rod is executing both rotation and translation. What will be the nature of unbalanced forces? Now, since there are 3 bodies, let us examine the problem for these 3 bodies. So, here the unbalanced force is simply the inertia force. Now, inertia force of a rotating object is nothing but the centrifugal force. So, therefore, the unbalance due to this crank will be nothing but the centrifugal force, which is m crank into E omega square. We have seen this in the previous cases of rotary unbalance. On the other hand, the unbalanced force due to the slider, which at this particular instant may be having an acceleration in this direction, say x2 dot. So, the inertia force of the slider will be minus m slider into x2 dot, but in the opposite direction. So, it will be in this direction. To find out the inertia force due to the connecting rod, we have to see what is the instantaneous acceleration of the center of mass. This we can call this as acceleration of the center of mass of the connecting rod, and also perhaps there will be some kind of an angular acceleration alpha of the connecting rod. At this instant, therefore, the unbalanced force produced by this, which will be felt by the support or the bearing structure, it will be m connecting rod into A G connecting, that will be the force, and it will also produce an unbalanced moment, which will be nothing but the moment of inertia of the connecting rod into alpha, opposing the sense of alpha. So therefore, you see that even for the simplest mechanism like a single slider machine or single slider mechanism, the total unbalance effect what this support of the whole machine is going to experience will be a rotating unbalanced force due to the connecting rod or due to the crank, a reciprocating or oscillating unbalanced force which is m slider into x2 dot at a particular instant, and x2 dot is continuously changing direction and magnitude. So this force also will be a fluctuating force, and a very complex force which is a force generated by the connecting rod, which is m connecting Ag at this instant, but this Ag of the connecting rod is also continuously changing and fluctuating. So this will be also continuously changing and fluctuating force, and the angular acceleration, you can see the connecting rod is making an oscillatory motion like this between its extreme positions up and down. So this will produce also a moment due to its angular acceleration at any instant. So it is a very complex situation. What we can try to do is have consider an equivalent system which is kinematically equivalent, but which is represented only by a purely rotating body and a purely reciprocating body. In other words, what I mean to say that we replace the connecting rod, which is the problem maker because it is a floating body, by two concentrated masses or particles placed at the two ends, that means here and here. Thus, what we propose to do next is so what we have done is we have replaced the actual connecting rod by a hypothetical connecting rod, and the hypothetical connecting rod consists of two concentrated masses at this end, which is Ma, and at this end, which is Mb, so that this actual connecting rod becomes dynamically equivalent to this, so that this distributed mass here is represented by two concentrated masses. But in doing so, we keep the dynamic equivalence intact. Now, what will make this dynamically equivalent to actual connecting rod? We say a particular object is dynamically equivalent to another object if same set of forces and moments produce the same set of motions. So how do we achieve it? Suppose a force and moment acting on this produce an acceleration of the center of mass and an angular acceleration of the object. So, a set of forces and moments produce an acceleration here and an angular acceleration. Now, the same set of forces when applied here should produce the same acceleration of the center of mass at the same location and same angular acceleration. Then we will not be able to feel the difference between this and this in matters of dynamics. Of course, there may be other changes, but so far as our discussion on unbalanced forces are concerned, it will not show its effect. Now, how we can achieve that? This equivalence will be possible when the total mass of the system, of the replaced system Ma plus Mb must be equal to the total mass of the connecting rod. That is number one condition. Number two condition is the location of the center of mass here and location of the center of mass here should be also unchanged, so that the moments produced about the center of mass due to certain acting forces also remain same. So, to satisfy that, so this ensures that the center of mass is at the same location as G connecting, and the same set of moment which now are produced about this should produce the same angular acceleration. That will be possible when the moment of inertia of this equivalent system about the center of mass will be same as the moment of inertia of the original connecting rod about its center of mass. That is, if I G connecting is the moment of inertia about the center of mass of the original connecting rod, it must be equal to this. So, now what we have done, we have placed two concentrated masses not at any two locations, but at this which we call the crank pin and at the slider. So, locations of A and B, that means where we place the concentrated masses, are fixed. So, therefore, and the location of G also we have fixed. So, what are the only unknowns available to us for our choice is Ma and Mb. Ag, Bg, they are all decided. So, if there are only two unknowns which will have to satisfy three equations, it is not possible, we know that. So, therefore, the only thing at our end which is possible is that we satisfy only two conditions out of these three and hope that the error introduced will be not very serious. So, it has been found that if we satisfy these two equations and this is not taken care of exactly, then the effect or the mismatch, dynamical mismatch between this and the replaced system will be minimal. So, therefore, what we do now onwards, we always treat that the connecting rod has been replaced by two concentrated masses, one at point A, other at point B, in such a way that its total mass is same and location of the center of mass also is the same. Moment we do that, our Ma and Mb can be calculated from these two equations. So, now what we have? We have a system So, now we have an object here, the original crank and a concentrated mass at location A, and this object is a purely rotating object. Then there is another matter which is here, which is the original slider and the apportioned mass of the connecting rod at location B. So this becomes a purely reciprocating mass. So the original system is now replaced by a system which is composed of a purely rotating object and a purely reciprocating object, which is definitely much simpler, and we will now attempt to handle this problem. From this point onwards, we should also keep in mind that if the force produced by this purely rotating force can be easily taken care of by placing a counterweight. So therefore, this counterweight placed at the opposite end of the crank will balance not only the original crank, but also the apportioned mass of the connecting rod MA here. So the only thing what remains that can produce unbalanced effect is this reciprocating mass, which is M reciprocating is the mass of the slider, original slider, plus apportioned mass of the connecting rod at location B. So therefore, now the only unbalanced force which will be M reciprocating into minus x2 dot, where x2 dot is the acceleration at this instant. Of course, you should keep in mind that x2 dot in a positive sense is in this direction. So your inertia force will be in this direction, that will be the unbalanced force. When x2 dot is negative, then of course this force will be in the other direction. So therefore, now we will have only unbalanced force in this system when the rotating part is taken care of by a counterbalance, is the only reciprocating inertia force. So next we have to find out the magnitude etc. of this reciprocating unbalanced inertia force, and to do that we have to have the expression for the acceleration of the slider, and next we will do that. So this is our problem. This is the slider mechanism. Now we are not bothered about masses etc. Our objective is only a kinematic analysis. What we have to find out is the expression for the acceleration of the slider at any instant, which is given by this angle theta when this crank is rotating at a constant angular velocity theta dot, which is equal to omega. Now here we know that this distance from the origin to the slider, which is x can be written as obviously On plus NB, and that is equal to how much is On? It is R cosine theta plus how much is this? It is L cosine phi. Now, theta and phi of course are related by the expression which we will just now see. If you drop a perpendicular from A on this line, so this length AN is equal to R sin theta and is also equal to L sin phi. So, therefore, we find that we can express sin phi as lambda sin theta, where of course lambda is equal to R by L. So, this cosine phi we can then replace, x will be then R cosine theta plus L into lambda, L into lambda, now therefore it will be L into 1 minus sin square phi, that is lambda square to the power half. And this we can write as x by R will be equal to cosine theta plus 1 by lambda minus lambda square now lambda square sin square theta is definitely less than 1, and therefore we can expand it in the form of a series. If we expand it, we will get equal to cosine theta plus 1 by lambda minus lambda by 2 sin square theta minus lambda cube by 8 sin to the power 4 theta, and so on. Now, I think there can be some trigonometric manipulation done, which I will not go into it, but you can show that x by R can be written in this form. What we have done is that in place of sin square theta, sin 4 theta, sin to the power 6 theta and so on, we have replaced the whole series in terms of cosine theta, cosine 2 theta, cosine 4 theta, cosine 6 theta, which can be considered as the various harmonic components. So, it is nothing but a series, that means where the x by r has been represented in the form of an infinite series with harmonic terms. So, this is the constant term, this is the first harmonic, this is the second harmonic, this is the fourth harmonic, this is the sixth harmonic, and so on. Now, to get our objective is to get acceleration. So, what we have to do? We have to differentiate this x twice with respect to time. Doing that, what we will get? So, after we have differentiated this twice with respect to time, we can express the acceleration in terms of an infinite series consisting of only the primary and then all the even harmonics. The coefficients of the various harmonics tells us about the strength of each harmonic, that means the amount of contribution that harmonic makes to the acceleration term. So, you can see even for a simplest possible case like a single slider mechanism, the acceleration of the slider is actually a complex quantity represented by an infinite series. Now, of course, if we have to work with this whole series, it is going to be a serious problem. What therefore we should consider is the practical situation. In most practical situation, the speed with which the cranks rotate, like say engines, normal engines, stamping machines or compressors. So, in such cases what happens? The speed is such and the lambda value is less than 1. So, we can ignore any term containing higher orders of lambda. That means, we can ignore from lambda cube onwards. Suppose if lambda is say 0.5 or say 0.3. So, lambda cube will be lambda cube by 4 will be 0.3 to the power 3. So, that is approximately 0.03 kind of thing and divided by 4. So, it is 0.01. So, it is 1%. So, immediately you can see we can ignore these terms. Moment that happens that we are considering only up to lambda, at the most lambda square, but lambda square is not here, and we ignore from lambda cube onwards, then A2 is equal to lambda. So, this then becomes simply lambda. A4 obviously then becomes 0. A6, which has the lowest order is lambda to the power 5, also 0. And so, therefore, we need not consider beyond this second harmonic. So, in such cases, that is also the situation with a large number of cases. So, in most cases, we can then express x2 dot as minus omega square r into cosine omega t you can see this angle is theta, which is nothing but omega t if we assume at t is equal to 0 crank was aligned with the cylinder center line, minus A2, or rather which is simply lambda we should write, omega square r cosine 2 omega t. So, this can be written as minus omega square r, sorry, let us write the unbalanced force now. So, the unbalanced force is given by a force which is equal to m reciprocating x2 dot. So, x2 dot is now this. So, minus sign goes. So, it will be m reciprocating omega square r cosine theta plus lambda m reciprocating by 4 So, you can see this is nothing but a harmonic force whose magnitude is equivalent to a centrifugal force where the reciprocating mass is placed at the crank pin and the crank rotates at its own speed omega. Then its component along the cylinder center line, that is x direction, is that primary component which we call the primary. This force, which is the second harmonics, we call the secondary, again can be considered as the component along x of that centrifugal force when a mass of m reciprocating into lambda by 4 is placed at the tip of the secondary crank. Now, secondary crank will be something of the same radius but which rotates at a speed which is double the speed of the primary crank, and which was of course aligned with this at t is equal to 0. So, this angle is automatically 2 omega. So, therefore, the unbalance of a single cylinder or single slider machine can be reasonably well approximated as a force along the center line, that is x direction, which consists of two components. One is the primary, other is the secondary. We will need to consider the higher harmonics when the speeds of operations are much higher, when the accuracy desired is much higher. For example, the aero engines and such cases, there of course it will be essential for us to consider the higher harmonics, but otherwise in most of the situations of engines and machines we did not go beyond this secondary component.